All right, so this is section 11.2, series. So we're going to go on top of what we just talked about last section is, what sequence is. Now let's talk about what a series actually ends up being when it comes to it. So the difference between a series and a sequence is a series is just the sum of all the entire sequence put together. So we want to find that sum of all things. You maybe think, well, isn't that just always going to infinity? And that's actually not the case. That's what we're going to be actually looking at here when it comes to it. So a series is of the form the sum of the whole sequence itself. So remember, this portion means sum. So essentially it kind of looks like this. So we like to take the sum from n equaling 1, like the first term, all the way to infinity, right? It just keeps going all the way to infinity of this series here. Okay. So this will be, if you plug in 1, you get 3 plus 1 gives you 4. Plug in 2, that's 6 plus 1 is 7. Plus plug in 3, that's 9 plus 1 is 10, and so forth down the line. Right. So that's what a series actually is. It's basically you're just adding up all the sequences together. So very, very same thing. We do the exact same process. You're going to plug in, except only this time we're just going to add up all the results together. Okay, and that's pretty much what it is when it comes to it. Now all we're going to do is, well, is there a way to find this sum? And that's going to be the difficult part we're going to be dealing with in this section. And again, we're going to have a couple of examples and scenarios how we're going to be dealing with this, and then some definitions to help us out. Okay. So here, given a series, let S of n be denoted as the partial sum defined to be this portion. So essentially what this is saying is there's some portion in this whole sequence that we have this sum accordingly. So it's like a part of the whole thing. Now here's the biggest thing when it comes to this type of definition is if the sequence S of n converges, meaning it goes to a single number, then the limit of the sequence equals S exists, then the series converges. The number S is called the sum of the series, and the sequence S of n diverges, the series diverges. So what it's saying is I'm going to take, instead of looking at the entire sequence itself, or series itself, I'm going to take a small chunk of it. So like from, I equals 1 to infinity, a good chunk. Instead of starting at 1, so let's say we start with 100. So we take, from 100 to there, and if we can find this converges, therefore the entire big one also converges to that a number. We don't know what it is, but we know it does converge to a single number. And I guess most cases we won't know what it converges, but it actually does converge or diverge. And vice versa. If we find a partial sum, again, let's say from 100 to infinity, and we don't find a conversion, right, it diverges, therefore the big one also diverges. All right, so this is a pretty important definition when it comes into play in that portion. Okay, so on top of that, we have a very special series, which you're actually going to be comparing a lot to, because it's a very popular one. It's a very easy one to comprehend. It's called the geometric series. Okay, so the geometric series looks like this. It's a sum from n equals 1 to infinity of a times r to the n minus 1 power. Okay? And it looks like this if you just follow along with the n, right? So where r is called a common ratio. Right? So an example would look like this. Sorry, 6. Okay. So this series would look like this. So it would be the sum of n equaling 1 to infinity. And notice they have the common ratio of 2. Right? 2 times something gives you 6. They're all multiples, are divisible by 2. So your common ratio, or in this case, the a value here is going to be 2. And then r is what's being powered, right? So for example, if we have r to the 0 power, that gives me 2, because 2 times 1 is going to be 1. Now what's the difference between here and there? Notice is 2 times something gives you 6. Well, that's going to be 3, right? So maybe we have a 3 being here. And notice that's always the same, right? So this is 3 to the first power times 2 gives you 6. 3 to the second power is 9 times 2 gives you 18. So this looks like that. And that's our geometric series when it comes to it. So again, the value r would be 3. That would be our common ratio. And the a value would be 2 in this case. Okay. Now, again, we're not going to go from here to there, but we're just going to be using this to illustrate that concept. So just a quick little example illustrating that. Okay. Now, the biggest thing is coming from these two here, is what we're going to be using a lot when it comes to the geometric series, is if, so this series converges if the absolute value of r, so this r value, is strictly less than 1. So again, the absolute value. Okay? So it converges. That's automatically known. And we also can find the sum of that series as well is equal to a over 1 minus r. Again, in this case, if it would converge, like say it's 1/3, you plug in a equals 2 and r is 1/3 if it was, if it actually converged. And if the absolute value of r is greater than 1, then the series diverges automatically. So it's a nice little portion when it comes to so we're always going to be using this one to help us out because it's a very simple case. We want to somehow convert our series to look like this, and then automatically we can use the geometric series to compare it to, and automatically get either converges or diverges respectively. Okay. So how will we actually do this? So let's try some examples using this fact. Okay. So given determine if the series converges or diverges, and if it converges, find the sum. Okay. All right, so the only way we know how to do this is very easy. Either you taking limits or somehow comparing it to the geometric series itself. Okay? So we have this going on here. So we know this is equal to the sum of n equaling 1 to infinity, and we can put the 5 out here, and this is going to be 1 over pi to the n power, right? That's another way I could write this. Okay. Well, the good thing is, if I take the limit as this goes to infinity, right, because this is one of the only ways we know how to do so far, well, by definition. Okay. Well, we know this all goes to 0, so therefore 0 times 5 gives you 0, which is great, so it converges. Okay, that wasn't too bad. Okay. So let's keep going. So this is what we have to use a geometric series for. However, you could technically try to. You would just dock it one value and pretty much get it from there. You would start at 0 and you would get it from here. But that's an easy way to do it, just by straight out the limit definition. But what's if, how do you convert it to use the geometric series? So let's just look at this one down here for the second one. Okay. So we want to find the sum of 5 to the 2n times 4 to the n 1 minus n. So since we have roughly 1 minus n or n minus 1 inner portion, right? In this case we have 1 minus n, and that's kind of similar to what we have here. Let's see if we can convert it or manipulate it in a way that we would just have a on the outside and some value raised to the n minus 1 power. Okay, so a lot of manipulation, a lot of algebra implied when it comes to these type of scenarios. Okay. All right, so we know I can somehow convert this to be 5 squared to the n power, right? That's just another way to write the first value here. Okay. Now let's also look at 4. So again, another way to write 4 is 4 raised to the, instead of 1 minus n, I'm going to pop a negative on the outside. Now make it look like that. Okay, so here's a little tricky what we're about to do. All right, so we know this is going to be 25, right? 5 squared gives you 25. So we have 25 raised to the n power. Now remember, here's a quick little note what I'm about to do. Remember, if I have a variable raised to a negative power, what that means is I flip it to make it positive. Now notice the same thing happens here. It's technically to a negative power, so what I'm going to do now is bring it to the bottom. And now I have that happening. Okay. All right, one more trick. Okay, so let's suppose we have x to the 5th power. Everybody agree that's the same thing as x times x to the 4th, right? I'm just breaking it down, right? Just 1 minus. So if you multiply these out, you get x to the 5th, right? You just add the powers together. So if I do the same thing for 25 here, if I just pull one out like that, therefore I now have 25 to the n minus 1 power, right? 1 minus it. I started with 5, I took 1 out, I dock 1, right? So that's why it happens here. Okay. Now notice this is exactly the same as that, because I could put these together, and now I have the sum from n equaling 1 to infinity of 25 times 25 over 4 raised to the n minus 1 power. And now it looks just like a geometric series, where a in this case is 25 and r is 25 over 4. And now we can compare it. So therefore, we know r is 25 over 4. And if we take the absolute value of that, that is definitely greater than 1, right? So this series diverges. And that's how we compare it to the geometric series. Somehow we use algebra to manipulate. So notice the whole work is manipulation, right, to make it look like that. And then compare it to our geometric series. Or compare the r value to see if it converges or diverges. Okay. All right, let's try some more. So this one is actually a doozy of a place. It's a very interesting question when it comes to this one. Okay. This is not really the norm itself, and this is the reason why I want to give you guys an example, because I believe you have one of these interesting when it comes to it, and I just want to get you guys aware how we do an alternative to all these three scenarios. Okay. So this is technically the same as 1 over n minus 1 over n plus 1. I'm just breaking up the fractions. Okay.